Wow, okay, I have not practiced this in a long time, but I only offered to do it because this is also an escape analysis talk. I've also not run this code in 125 yet, so this is going to be super cool. So let's start with a story. All right, so way back in the day, when I was a very young gopher, everybody was talking about how cool the IO package was. It was like the best package in all of the standard library. The sad part was I've never been able to work on anything related to streaming, so I never got to play with this particular package. So I decided that I was going to create a problem so I could start learning this API. And the idea of the problem was I was going to search the internet for the name Elvis. And everywhere Elvis's name was not spelled with a capital E, well, I was going to fix that, damn it, because he's the king. We're not going to allow that to happen. Now, again, remember, this is the first time I'm ever trying to do anything like this. So I created a little table just to get a little test run in there. So everything on the left is the input and the expected output. We can assemble that into a stream. And then I turned around, and within about 20 minutes, I wrote this code. I was actually quite happy with this code. Started with a buffer, found the length of 5, created a little buffer of 5 bytes, read the first 4 bytes in, and then I went into a little loop and kept sort of adding a byte to the end of it, checked if it was equal. If it matched, then I would fix Elvis, and if not, I'd keep going. Again, my first attempt at this. I was proud. It worked. So then I jump out on Twitter, when it used to be called Twitter, and I asked the Go community, hey, how would you solve this same problem? Got a bunch of entries. Well, my friend Tyler from Salt Lake City turned around and he gave me this function here. What Tyler decided to do was use a new reader. He got the length, started at index 0. Then he started reading 1 byte at a time. He kept checking each of those bytes. And if he ended up getting a match, 5 matches in a row, then he'd write out the replacement for Elvis's name. And if not, he'd unread it and he'd keep going. And I said, Tyler, this is amazing, dude. Like, I never thought about, have you done this before? This is cool. But Tyler, have you benchmarked this algorithm? He said, no, I haven't benchmarked it. I said, well, this is pretty cool. I've got 2 algorithms that are solving the same problem. Why don't we write some benchmarks and see sort of how these 2 algorithms compare? So I went ahead and I wrote these 2 benchmark functions. There they are. Algorithm 1 is mine. Algorithm 2 is Tyler's. And I went ahead and I said, okay, let's run some benchmarks here. So I'm going to come over here and we're going to run the benchmark. I might need to make this a little bit louder. All right, because algorithm 1 is mine. And I run this, and I'm like, Tyler wrote a 0 allocation algorithm. So I called Tyler right away. I said, Tyler, do you know what you did, man? No, like, nobody writes 0 allocation algorithms out of the box. Dude, this is amazing. And then I hung up the phone, and my brain went, you know what? I didn't write a 0 allocation algorithm. I'm the one who teaches this stuff every day. Now all I feel is that Tyler has thrown down the gauntlet. Tyler has made me look bad. And I have one decision now. I have to make my algorithm run faster than Tyler's. Now I've got to figure out how to do that. Obviously, there's 2 allocations happening with 53 bytes of allocation. So I figure if I get rid of those allocations, if my algorithm could be 0 allocation, maybe I'll be faster than Tyler's. So we've got to figure out now, what's going on with these allocations. All right, not a big deal. What we'll do next is we'll go ahead and we'll ask for a memory profile. So I'm going to run the same benchmark. Yes, I've got to watch Tyler beat me again, but dude, I'm coming for you. No big deal. And I've now run it again. And now what I have is a p.out file. Okay, sweet, no problem. What we're going to do here is go tools pprof, p.out, come over here. Now I'm going to stay inside the terminal. And remember that it's algorithm 1 that I care about. So I'll do a list, algorithm 1, and boom. Okay, I've got some information. There's 2 allocations going on. Obviously, something's happening on line 83, something's happening on line 89, and it looks like what we've got there is a flat allocation on 89. That's the first column. That's telling me that it's that line of code that's causing the allocation. But I got the cumulative allocation on line 83, and that's telling me that what's happening is that something going on inside of new buffer or that call chain is causing the allocation. Now, this is fine. This is somewhat telling me kind of where to look, but it's not really telling me sort of what and why this is going on. I need more information. Well, luckily, the compiler can give us an escape analysis report. It can give us some more information about what's going on. So if I just ask for that related to everything that we have here, we should have enough information to figure out what's going on. Now, in order to get that escape analysis report, what I'm going to do is add the GC flags minus M2. That will give me a level 2 report. And I'm going to put everything here in the terminal. So again, one more time, Tyler, don't worry, those are going away very, very, very soon. So we're going to do that. I'm going to do so I've got the escape analysis report. I'm going to bring this back up. And I've got everything I need now to figure out what's going on. Okay, what line is that? That's in a file called stream.go on line 83. No problem here. Let's search for let's spell it right though. Stream.go:83. We'll look for everything. And I kind of see something right here that's already sort of interesting to me. It's telling me that this function is being inlined. It's actually not getting called. Well, if I go back and I look at our report, that's sort of not being suggested here. This output is suggesting that the function is being called, and whatever's happening under there is causing all the pain. Let's do a couple things first, though. Let's take a look at that function. So where is that? Line 83, sort of there it is. And if we sort of go into the definition of it, you can see it's fairly simple. It's just constructing a value, and it is sharing it back up the call stack. So for sure, if this function was being called, that would be an allocation. Based on the way the escape analysis would say that value can't stay on the stack here because that stack frame's going away. But the report's kind of telling me that that's being inlined. Now, what inlining basically means is this code is being taken out of this function. The function call is being sort of replaced, and the code, I could fix it up, is being inlined in there. So why is the report not showing me that this is actually a flat allocation and not a cumulative? Well, I could do this and look at the browser. Oh, what was that again? There. Okay, that wasn't right. How do I get the browser version of this? It won't even matter since I can't remember. Okay, I can't remember what that is. Anyway, I'm going to show you something here. I'm going to run this again. Let me run everything again. But I'm going to flip a switch on the console side here. And this is I think it's a bug, but the Go team won't agree with me here. Go team, you guys don't agree with me here. Well, that's okay. What's happening is when we look at this tool using the terminal, it has all that sort of inlining turned off. That optimization is not being shown. But if I use this switch that says no inlines, it will show me the inlines on the terminal side. So now if I do list alg1, it is suddenly flat. Now, if I could bring up the browser version of this, and I don't know why I can't remember the name of it, we would have seen that. So the browser version keeps this optimization on. The terminal side sort of keeps it off. This is for my purpose, this is a more accurate view of what's happening. You can see it really isn't cumulative. It is flat here because of the inlining optimization. The value is being constructed there on line 3. Okay, that solves that particular problem, but I still don't know why it's happening. So let's go back and continue to look at this. Okay, there's some interesting information here. In fact, this right here is really interesting. It's telling me that on line 93, there's some sort of interface conversion going on. And what it must mean is that this value that we're constructing is getting probably assigned to some interface, and that's causing the allocation. Let's take a look on line 93. Well, there it is right there. Remember, I wanted to learn how to use the IO package. That's the read full function. How does it accept the concrete data through an interface? That's polymorphism. And what's now happening is that when we pass the concrete data that we constructed on line 83 into this function, now the compiler says that value has to be on the heap. Now, why does Tyler not have any allocations? Well, Tyler was smarter than me. If you really notice the code that Tyler wrote, he constructed the reader. He's going to get an inlining optimization here. But then he uses the method set of that for the rest of the function. He's not using the IO package. Tyler cheated. Now, I don't care about IO packages anymore. All I care about is being faster than Tyler. So if we get rid of the IO package and go back to the method set, I bet you we can get rid of the allocation. All right, so let's sort of see if we can figure this out here. So what we're going to do is we're going to say input dot, and that's going to have the read. I could probably get away. Man, it's been so long since I tried this. Let's see. So if I put this in here, all right, so that's going to be that read. And I'm going to have another one of these down here. So I should be able to do that. Now, this one's a little more sort of tricky because here we're going to have to do that input.read byte. And that byte needs to get to sort of the end of this. This all gets a little tricky. But if I can remember here, we'll do that. And then we'll have the if error doesn't equal nil. And I can get rid of sort of all of this. And that sort of should get me there. And of course, I don't remember how to do this anymore because it's been so... Oh, no, 0, 0, 0, 0, 0, index. Come on, Mr. Kennedy. Okay, so that's equivalent to what we had with the IO package. There is no more use of the IO package, no more interface. I should at least get rid of that one allocation now on line 3. We're going to try it. So here we go again. Going to run that. Okay. Whoa, look at that already. Out of the box. I got no allocations. I just lost 2 of them. I was only expecting 1 to go away. I'm still quite slow though, am I not? I don't feel like I got much out of that. But how cool is that, right? I was able to use the escape and I really don't know why I didn't get another one, but let's take a look there. I want to run this again. Yeah, really wild. Okay, so what's happening now is I am running as a 0 allocation algorithm, but I feel like this code is not running right for some reason. There should still be 1 more allocation in the mix, and that's going to be this right here. We should have had that before. So I'm going to do the following real quick. Let's put this back. Let's put all this back the way it was. And I'm going to run this again. We're back to the 2 allocations. I want to look at the allocation that we had before. List alg1. I want to look at this one on line 89. I'm not 100% sure why that disappeared with the last change, but let's just roll that one back for a second and come back to this. We know why we have the allocation now happening on line 83. It's because of the IO call in the interface. But why do we have an allocation happening on line 89? All right, let's just take a look at the escape analysis report again. That's 89. All right. Let's see if we can find something about 89 here. Let's see here. Now, what I'm expecting to see, and I'm not seeing it, again, this report could have changed the last time that I looked at it, and I'm not seeing it. But ideally, what's happening here is that if the compiler does not know the size of a value at compile time, then it has no choice but to allocate that on the heap. It doesn't know how much sort of stack space to sort of leave for that. And if you look at what's happening here, that variable size, we're setting it right here to length. Compiler has no idea what the size of that backing array is supposed to be. I would have expected to see it somewhere in here. It used to say to you, hey, unknown size. I don't see it. I'm looking for it. And that's okay, because we're going to do the following. If you don't tell Tyler, I won't tell Tyler. I'm going to do that. I'm now going to tell the compiler that what we really need is a backing array of 5 bytes there. Just this alone, if I run everything again, oops, let's run the whole thing again. Wow, this is not doing anything that I've ever seen before. I should have seen. So it looks like something new in 125 is this doesn't matter anymore. So kudos to, oh yeah, Keith, tell me. There you go. So he's saying allocations under 32 bytes will happen on the stack even if you don't know the size. Wow. So you magically know that's not 32 bytes. That's brilliant. But that being said, Keith, who's about to come up here and talk with me, then why am I seeing a flat allocation, Keith, on line 89, which would represent the fact that we don't know the size of the backing array? Ha 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 ha. Somebody has their hand up. Ah, okay, that's fair. That is fair. So this is no longer a fun talk for me. Because I can't have fun with this one anymore. Because now when I got rid of, now Keith and I are going to sit after this. But look, even though everything is just completely melting down here, it's okay, right? Because the big point I wanted to show you, since there was supposed to be an escape analysis sort of talk up here, was this. Look, you could do this with Go test because everything has to be built ahead of time, and then that build will take on the escape analysis report. You can do this with Go build. But look how sort of cool this is, right? The point here is that you don't have to guess what's going on. If we run that benchmark and we see these allocations like we did, we saw these allocations, right? With the escape analysis report, we can see things also like why a function didn't get inlined. Every function gets a complexity score. That score is 80 or less there, budget 80, then it can be inline. You might have a function that's in sort of some tight loop, and you really want to make sure that we're not taking the extra cost of the function call. Maybe you can come in here and start figuring out how to sort of reduce the complexity of that particular call. And like I said, when we went to and looked at stream go : like 83, we start to see, yeah, there was an inlining there. Yeah, we are allocating because of that interface conversion. And you saw when I got rid of IO call, though I expected it to be a little bit faster. How fast is it right now, actually? How fast was it? Yeah, 6. So remember when I changed that code, it went down to 300. So I cut it in half, but Tyler was still like running 100% faster than me. So if I were to put that code back and we were at 300, I still wrote a 0. I didn't even get a clap for a 0 allocation algorithm change, man. That's unbelievable. You clapped for Tyler. Oh, Tyler's in trouble. But you saw it. You saw a 0, right? I don't care. I have it on video. You can lie all you want. But here's the funny part, right? Here's the funny part. If I put the code back, and now I'm running at 300 nanoseconds an op, even though he's still running almost like 100% faster than me, I could now start looking at a CPU profile, couldn't I? I could start seeing, okay, from a CPU perspective, why am I running slower? Now, if I had done that, what you would have found in the report is that that bytes.equal call is actually killing me. But look, here's the real sort of moral of the story, the one that I really want you to take back with you. We're talking about 400 nanoseconds, dude. What am I doing, man? This is going to make no change in anybody's life related to this software. This was all about my ego. 400 nanoseconds was all about my ego. How ridiculous was that? However, if you get yourself in a situation where you've got to do this sort of micro level, analysis and benchmarking, now you know how to do it. The tools are just there. Go is amazing with the tools. And never try to do this in 125 unless you've done it before. And you don't have Keith mic'd up. Anyway, we had 3 minutes left though, but I'm going to leave you guys, take a little break for the next talk. Thank you for hanging out with me.